Hello, everyone, and welcome to this workshop session of Very DevOps. My name is Mikael Salari. I'm a PhD student at Mälardalen University. Today, I'm going to present our recent publication, which is titled An Experiment in Requirements Engineering and Testing Using EARS Notation for PLC Systems. This paper has been published recently in AMA's workshop of the ICSC 2023 conference. And the actually corresponding authors are Eduard Paulinoio, Vasif Afzal, and Cristina Secheleno from Mälardalen University. Let's start with the introduction and motivation. As you might know, regulatory standards for engineering safety critical systems often demand both traceable requirements and a specification-based testing during the development process. And we know that engineering safety critical systems also usually obey regulatory standards. And we know that traceable requirements and specification-based testing are both required during the development. Since the requirements are often written in natural language, as my colleague Andre also explained some minutes ago, yet for specification purposes, this may be supplemented by formal or semi-formal descriptions to increase the clarity of the requirements. However, the choice of the notation of the semi-formal descriptions is often constrained by training, skill, and preferences of the designers. What is EARS? EARS actually stands for Easy Approach to Requirement Syntax. It's a simple notation for writing textual requirements. It was firstly introduced actually at Requirements Engineering Conference in 2009. We know that Rolls-Royce Company and Intel are using this actually syntax for increase the clarity in the requirements to also reduce the main problems detected in stakeholder requirements. And we know that they actually EARS can address the inherent imprecision of natural language requirements, and it can somehow eliminate potential ambiguity and also lack of accuracy. What are the research goals of this actually work? This work, we know that it actually tries to investigate about requirement specification using EARS patterns, and also a specification-based testing of embedded software written in two IEC 61131-3 standard languages, including function block diagram, which is some kind of graphical programming language of PLC programs, and the other one is a structured text. So, based on the research goal of this study, we conduct experiments to study how participants translate natural language requirements into EARS. And also, we are interested to see how engineers use EARS requirements to test the PLC software. Based on this research goal, we actually formulated three research questions. The first research question is that how are the EARS semi-structured requirements, engineering syntax, and test creation applied in the context of PLC programs? The second research question is what EARS patterns are used during the writing of the requirements? And the final research questions investigates about this thing, that what challenges are perceived during the specification of requirements and test creation using EARS. So we report our observations during the experiment, and also these observations include the type of the EARS patterns participants were more interested to use when they wanted to transform these natural language requirements into EARS semi-formal requirements. We also observed the challenges they actually faced during this specification phase, and also we present the results of testing PLC program based on the EARS formalized requirements. I will give you actually a brief introduction of PLCs, why they are important and what are PLCs exactly. PLC or programmable logic controller devices play a significant role in today's automated industry. And we know that PLC devices are being widely used in safety critical applications such as power plants, nuclear plants, and cranes. And we believe that using a semi-structured, easy to understand requirement syntax, such as EARS, may improve the quality of PLC testing and requirement engineering in industry. So let's talk about the experimental setup overview in this work. We know that we actually conducted a controlled experiment with participants. We gave the participants three requirements basically using EARS syntax. They had the freedom of choice to actually use the preferred EARS syntax template they like in this experiment. The subjects in this experiment were 10 individuals, including 4 experienced engineers at a large automation company in Sweden and also in Spain. And we actually had 6 researchers and managers from different universities and research institutes across Europe who participated in this experiment. For object selection, actually, we had a manual choice based on these criteria on the requirements. So we were more interested to actually choose the requirements that are actually in natural language that are understandable for the participants. And we know that these requirements should be sufficiently rich in detail for an engineer to write executable test cases. We know that they should represent different types of real testing scenarios in different areas using IEC 61131 standard. We know that these requirements must be simple to understand without any domain knowledge, and the resulting test cases in the PLC testing part of this experiment should be executable in Codesys environment. So let's have a look at the natural language requirements that we used in this experiment. We used 3 requirements, as we call them RI or requirement ID number 1, RI2, and RI3. How we found these requirements, we had an investigation in industrial libraries provided by a large company in actually context of PLC systems. We identified 3 candidate requirements, as you see here, that match our criteria, the criteria that I talked about in the last slide. We selected high-level requirements that are not trivial and fully manageable within 60 minutes, which was the time budget of this experiment. And also, we know that these actually requirements should not require domain-specific knowledge. So the first requirement says that user accounts should be uniquely identified to a user. The RI2 or requirement ID number 2, it says that the software shall warn the user of malware detection. And the third high-level requirement we have in this experiment mentions that only authorized devices are allowed to connect into the industrial control system network. So before actually jumping to the section that we want to have a look at the results of this experiment, let me talk a bit about the EARS templates that are provided by the actually designers of these patterns in requirement engineering syntax. The first is template called ubiquitous requirement, which we call it U in this experiment. It is a type of requirement that is not bounded to any preconditions or triggers and is always enabled in the system. And you can see the actually way we can write it is pretty straightforward. For event-driven requirements or ED, we know that we will use this pattern only when an event is identified in the system. And for the third one, we have the unwanted behaviors pattern or UB, which refers to covering all possible situations that are not desirable and are usually a big source of omission preliminary requirements. We have 2 more patterns. The first one is a state-driven requirements or SD, which is only active if the system is in a specific status. And finally, we have the optional features or OF is template, which is designed to be used when the author of the requirement wants to include a specific feature in the system. We actually observed some challenges during this actually process during using EARS template, we observed that actually the challenges that encountered during the specification of the requirements, and also the challenges that happened when designing test cases for PLC systems in the second part of this experiment. We also applied thematic analysis for qualitative data to extract the main themes as reflected by input given by each participant in this experiment. So let's talk about the instrumentation of this experiment. We organized one session. The subjects were given tasks to use three requirements that I talked about in the last slide and rewrite them in EARS format. The subjects were not grouped, of course, and both digital and written forms of the needed experiment document were provided to them. A short tutorial on EARS syntax was provided to the subjects within 10 minutes time budget, and also the data collection procedure happened in this way. As part of the instruction, subjects submitted their solutions in form of the coded document, and also data from this experiment session was then used for quantitative and qualitative analysis. After having a look at the results we gathered from the participants in this experiment, we actually reached this conclusion for actually the EARS patterns the participants used in this experiment. We noticed that for first requirement, or RI1, most of the participants preferred ubiquitous actually pattern, and one of the participants tried to transform this requirement using both ubiquitous and also unwanted behavior actually patterns. For second requirement, or RI2, we noticed that event-driven and unwanted behavior were the most popular patterns that were used by participants. And for actually third requirement, we noticed that unwanted behavior were the most preferred pattern to be used, and then event-driven and state-driven. So we have some information here in terms of the template used by each participant, which shows each participant, which called here P1 to P10, use which kind of EARS patterns in transforming the natural language requirements, for example, RI1 to EARS requirement. And also it is the case for the RI2 and 3. So based on the results of this experiment, we applied the thematic analysis to extract some main themes related to the approaches and challenges encountered during this translation process. The first main theme we notified is that requirements are not complete and clear enough for EARS translation. The second main theme actually mentions that using single or multiple EARS template is not clear enough, especially when using these for testing. We know that the system perspective is not easily identifiable from the requirements. And finally, we noticed that the optional feature template is not applicable for the selected requirements at all. In the second part of this experiment, we tried to test PLC programs based on the concretized EARS requirements. So we used 3 PLC programs that implement the behavior of the selected natural language requirements. And all of these PLC programs were developed in a structured text language. The PLC ID we used in this experiment was Codesys version 3.15, which is very popular in industry. We used the testing tool called Codesys Test Manager, which is the official testing tool of actually Codesys. On the right-hand side of this picture, you can see some snippets of these programs that we use, but it is not like the full picture of them because they are much bigger than this. So here I want to show you the workflow of the PLC testing methodology that we use in this paper. First, we had that 3 natural language requirements that I mentioned before. And if you follow this star in this picture, we applied the EARS syntax to have some concretized EARS requirements to make the requirements more understandable and comprehensible for the tester before generating test cases based on them. Then we generated test cases based on these concretized ears requirements that we had in this experiment. And after actually executing these generated test cases automatically using the Codesys test manager on 3 different PLC programs and checking the expected output, we actually finished this part of experiment, and we will see if they look actually applicable in field of PLC testing or not. So I want to show you the concretized ears requirements. When we say concretized ears requirements, what does it mean? For example, for the requirement number 1, we can see that it says that the user account system shall identify the user. If the user is not identified, then user account system shall alert. We have followed the pattern of the ears in this actually one. And then when we want to concretize it for a tester, PLC program tester, we modify it like this. We say that if unique ID equals to false, we follow the Boolean logic of PLC programs, then unique user account, which is one signal in the system, shall put false as the actual value of the result unique, which is the output. So we did the same thing for requirement ID number 2 and 3 when we transformed them to signals in PLC programs to clarify the requirements for the tester to avoid any ambiguity and problems in generating the test cases. After generating the test cases, we use the Codesys test manager, as you can see in this picture, to import, to actually design the test cases and also execute the test cases automatically on these PLC programs. In the upper picture here, you can see, for example, the different scenarios that we had for first requirement, the variable address in the system, its directory, and the value, and the action we used here, for example, is write variable. And in the bottom picture, you can see the results of the test execution. So the test results of the PLC programs are mentioned here, but I will try to just focus on maybe one of them because for the rest, I can refer you to the reading the paper. It would be out of the patience of the audience of this presentation, I believe. So for test results of, for example, PRG1, which we know that investigates the user identification, we designed 2 test cases to cover the user identification scenarios. And each test case, we know that includes the following 2 test actions. We call it test action in Codesys environment when we want to use the Codesys test manager. So we know that we use 2 write variable test actions to alter the actual value of the user and user account inputs. And we use 1 compare variable test action that compares the actual output with the expected output to see if the test case will be successfully passed or not. We use after applying the actual test execution automatically using test manager, we noticed that it happens, it's actually done in 0.3 seconds, and which is quite fast, and all executed test cases have successfully passed. It was the same for PRG2, which was about the malware detection, but the test execution time was a bit bigger because the program was a bit more complex. And it was the same for the third one, and all the test cases actually successfully passed. I want to conclude actually this work in this slide. As I mentioned, we have conducted an experiment in requirements engineering and testing using ears notation for PLC programs. It was the first step, and we want to investigate more about this actually area. And we know that in the requirement engineering part of our experiment, we found out most participants prefer the ears ubiquitous pattern for transforming the RI1 first requirement from natural language to ear syntax, and the unwanted behavior and event-driven patterns were the most popular ears templates for second and third requirement transformations. We also observed what was very interesting is that we also observed that different individuals use different ears patterns for transforming the same requirements based on their personal interpretation, which implies an acceptable level of flexibility in ears syntax. And in the testing part, we noticed that we investigated the applicability of using the EARS patterns in terms of PLC testing, and the gathered result of test execution implies that using EARS in creating requirement-based test cases for PLC programs looks promising, but it needs more investigation. And EARS can benefit actually the PLC testers by establishing an easy-to-understand way of expressing the test specifications. For future work, we want to do the more investigation by applying it on other levels of testing and by including more PLC programs. And we want to investigate the impact of choosing different EARS templates for describing the requirements over the quality of the generated test cases. And we are thinking about automating our solution and generating test cases from the EARS requirements based on existing functional and non-functional requirements. So with this slide, I will finish this presentation, and I want to thank you for your attention, and I will be happy to answer any possible questions.